board. Okay, here we go. All right. So we're beginning our discussion of energy. We're going to talk about two kinds of energy. Energy caused by the force of gravity and energy caused by motion. So it looks like some people have not opened the lab yet. We need to open the lab. All right. So before we read through this, I'm going to draw some diagrams that we're going to connect to this handout. So you're going to need to grab yourself some paper. Remember, you can use your lab notebook. You can use a blank piece of paper. You can use whatever you want. I'm actually going to use a printout of our handout. All right, so I'm going to stop sharing. I'm going to switch my camera and we're going to get down to brass tacks and we're going to talk about energy using free body diagrams. Okay, here we go. I'm going to shrink humans and give us a little more light. Okay. So we are going to read through this obviously on our own in a minute. This lab and the final lab of the class have both a physics component and a design challenge. So don't stress if that worries you. An example of a design challenge was when we made a second parachute to improve it. Okay, that was an example of an engineering challenge. We will have one of those with this project as well. All right, so everybody say KE. KE. All right, KE in this story is kinetic energy. So everybody also say kinetic energy.
Kinetic energy.
Kinetic energy, okay? So KE in this story is kinetic energy. I'm just going to go ahead and write it right here. Kinetic energy. Everyone say PE. PE, okay? PE is potential energy. Everyone say potential energy. Potential energy. Now, we're going to talk about another kind of potential energy in our final lab for the semester. In our story, we're talking about a very specific kind of potential energy. We are talking about gravitational potential energy. Gravitational potential energy. All right, so hopefully you got stuff that you can draw a picture with, because that is what you're going to be doing right now. The first thing we're going to do is draw a picture. So I got my handy protractor, which sadly broke, as you can see. All right, and we're going to make a free body diagram of marbles moving down a slope. Okay, so in this lab, we're going to be building a roller coaster. And your roller coaster is going to have several slopes. It's going to have 3. So I'm just going to draw a picture of what my roller coaster might look like right here. You're going to do the same thing. Okay. All right, so this would be a roller coaster that has 1, 2, 3 down slopes and 1, 2 up slopes. Okay, it might be very similar to what you design in this lab. So our roller coaster car is going to be a marble. So everybody draw a marble on your roller coaster. All right, give you a moment to do that. So Ethan,
Yeah.
What is the force that moves the marble down the slope?
Gravity.
Yep. And where does it pull? What direction does it pull in?
Down.
Down meaning straight down, right?
Yep.
Towards the center of the earth. Okay, so we all have to draw gravity. Force of gravity pulling towards the center of the earth. So that's FG. Force of gravity. All right. Bridget, do you remember the name of the force that a slope puts? Well, name one of the forces that the slope puts on the marble.
Friction.
Great. Force of friction. The force of friction resists the motion of the marble. And I'm going to draw it here just so it's easier for space. All right. The force of friction is going to move this way. Eli, what is one more force that the slope puts on the marble?
The normal force.
Yes, normal force. So normal force acts perpendicular to the surface of the marble and the force. Or sorry, surface of the marble and the surface of the roller coaster. That is called normal force. All right. So I've tried to draw the length of the arrows to indicate which force is obviously greatest. And when you put the marble at the top of the slope, it's going to roll down the slope. And so the force of gravity, the net force is actually, so this is the sum of all forces. The net force on the marble is actually going to be in what direction? Bryant.
Downwards?
When you say downwards, though, do you mean downwards this way?
Yeah. Well, no. I mean going down forwards. So
Would you say parallel to the slope?
yeah.
Yes. So the net force, right, which would be Fg plus Fn plus FFR is going to be, so we've got down, we've got this, we've got that. The net force, if it accelerates down the slope, is actually in this direction. Okay, we've never done that before. I want to point this out. How can I tell that the net force is parallel to the slope by watching the marble after I let go of it, Chris? How can I tell that that is the direction of the net force when I watch the marble on the roller coaster?
It's moving down that way.
Yeah, it's moving down that way, right? It starts, its velocity right before I let it go is what, Chris?
0.
0, okay? And it's going to increase velocity in this direction. That is called what? As if it's changing velocity in this direction, it is doing what?
Acceleration.
Yeah, acceleration, right? And acceleration is always in the direction of the net force. So if I watch something speeding up in a direction, I know which direction the net force is pulling in. Class, that was a brilliant collection of physics ideas. I'm very excited about that. Okay, so back to our story. Marble rolling down a slope, okay? At the bottom of the slope, the direction of the gravity stays the same or changes, Ethan?
Changes.
The direction of the force of gravity.
Oh, just stays the same.
Yeah, you were all up in net force in your mind, but which is where I'm getting to. But I'm going to make you the gravity guy for this story. Okay. Yeah, the direction of gravity stays the same. Eli, direction of normal force, has it changed? It's always perpendicular to the contact surfaces.
So no, it didn't change.
Well, the contact surfaces here are like this. So a perpendicular arrow, does it go in this direction still?
No.
So has it changed?
Yeah.
It has. Normal force is now in this direction. Lydia, has the direction of the force of friction changed?
Yeah.
What direction is it moving in? Describe it in relationship to this slope.
Like parallel to it facing the marble.
Yeah, exactly. Parallel to the surface facing the marble, force of friction. Okay, great. Whew. So we've got this situation on a roller coaster where at different points in the motion of the roller coaster car, which is represented in this case by a marble, our forces are changing direction. So, Chris, I can say if this slope is relatively straight, that on this slope, acceleration is relatively constant along this part. Why could I say that as far as the forces are concerned?
Because there's no changes in the slope and how it's formed, I guess.
And so, yeah, and so the direction of the forces isn't changing. Bridget, when I get to this point, has the acceleration changed?
Well, it stops.
Well,
Oh no, because it's on a roller coaster. I get you.
yeah, it's not going to stop. But is its acceleration going to change? As,
Yes.
And that's because the direction of what has changed?
The direction of the ball.
Oh, yeah, that's true too. But no, I want to talk about forces.
Okay, so which force has changed when it hits that point?
Yeah, which forces have changed? Direction of which forces?
I don't know.
Well, I'm looking at this drawing and I'm looking at that drawing. And all you have to do here is tell me which arrows have changed direction.
Oh, that one that's pointing diagonally on the first one and upwards on the second one.
Yeah, what are those called?
Normal force.
And
I don't know, man. It's very small.
it's FFR.
Oh.
Normal.
So normal force and FFR.
Which is
Yeah.
called the force of.
That's a really good question. Friction?
Yeah.
Okay.
Yeah. I feel like other people said that. I feel like you were the one that identified friction originally.
I was the one who identified friction.
And then I labeled it.
My
Yeah.
job is done.
You forgot what you said. That's hilarious. Okay. Yes. Yeah. So if the direction of two of these forces changes, it's going to change the direction of acceleration. Does everybody follow the story? It's going to change the net force. It's going to change the direction of net force. It's going to change the direction of acceleration, right? So this is the net force for our first drawing. Right? But the net force, directional net force, is going to change throughout the roller coaster. Okay. But remember what Chris said. Chris said along a straight slope, acceleration is constant. But then when it comes here, acceleration changes direction. Now, as it goes up slope, is acceleration, Lydia, going to be causing the marble to speed up or slow down on its way up the slope?
Slow down.
It is, right? On its way up the slope, we have force of gravity in this direction. Force of gravity is preventing it from going up the slope. Normal force is preventing it from going up the slope. And the force of friction is slowing it down, okay? So we go from a situation where the net force is pulling it down the slope. I should number these. 1. Shoot, I shouldn't use a circle because there's marbles. That's very confusing. All right, this is drawing part 1. Let's do drawing part 2. I should have drawn this bigger. I get that from what Bridget just said. Sorry, y'all. Okay, drawing number 3. So this is the sum of the forces number 1. And I want to do the sum of the forces number 3. The sum of the forces are still force of gravity, which is pulling this way. The normal force in 3 now is pulling this way. Zoop. Okay, and friction in drawing 3 is going that way. And the sum of our acceleration, therefore, is in this direction. It is slowing down. So I put acceleration here, okay. Okay, so long story short, and why we give a crap is though acceleration is relatively constant, on a straight slope, because the direction of forces is changing, acceleration is not constant, along the marble's entire route. This is going to become important probably by Monday's talk. But this is extremely important. You need to write this down somewhere. Heck, if you already made a Google document, you could just type this bugger in. It's going to have to be stated somewhere in that introduction. It's critically important to the cool stuff we're about to do. So though acceleration is relatively constant on a straight slope, because the direction of forces is changing, acceleration is not constant along the marble's entire route. Okay, now let us introduce energy. Okay, and this is related to this diagram or this equation we have right up here. So, energy at the top and energy at the bottom of a slope. So now we're just going to draw, so new box, new drawing. We're just going to draw the slope. We're just going to look at the marble on one slope.
Hey, Jarrett, what were the last 2 words of that?
Oh, entire route.
Okay, thank you.
You're welcome. Okay, so we're only going to look at one slope. So everyone say gravitational potential energy. Gravitational potential energy. Okay, so when you have an object that could get lower on planet Earth, it has what's called gravitational potential energy. Okay, so this marble, does it have gravitational potential energy, folks? Could
Yes.
it get lower?
Yeah.
It could. Okay, so this marble, it has potential energy 1. It's in position 1. So in this formula up here, that's potential energy 1. It's going to roll down the slope. When it gets to this point here, is Fev here yet? Oh, okay. Lydia, when it gets to this point here, can it get any lower on the roller coaster?
No.
It cannot. Okay. So at PE2, its gravitational potential energy equals 0. So there is an equation for gravitational potential energy. It's actually quite cool. You can measure the gravitational potential energy of an object by simply knowing its mass and how far away from the ground it is in meters. All right. So we've got a couple of things we're going to want to label here. So this here is the height. It's the height of the slope. Okay, and we're going to want to indicate it in meters. So please label that. You've got a marble. It has potential energy 1 at the top of the slope. And at the bottom, it has potential energy 2. This here is the height of the slope, okay? And this is the marble's displacement. Okay, so S here is displacement, as it always is. The marble is going to roll from here to here. And so this distance on the slope is its displacement, and this distance is its height above the 0 position on the roller coaster, which is where it cannot get any lower. Okay. So potential energy 1 equals the marble's mass times its height times acceleration due to gravity for all objects on Earth. Can anyone tell me what acceleration due to gravity for all objects on Earth equals?
9.8 meters per second.
Excellent. G equals 9.8 meters per second squared. Okay. So that's a constant. That's just a number. That's easy. So Chris, what is the marble's velocity at the beginning?
0.
It is 0. Okay. So this marble has a gravitational potential energy, which we wrote the equation here. PE equals gravitational potential energy. Potential energy. All right. And it has a KE. KE is energy of motion or kinetic energy. This equals kinetic energy. Whoops, which I just misspelled as if I don't teach physics. Kinetic energy. Okay, this is energy of motion. So if its velocity is 0, Chris, what do you think its energy of motion is? Probably.
At the beginning,
Yeah.
0.
Yes. So at the beginning, KE1, it's going to equal 0. The formula for KE is 1/2 the marbles times the marble's mass times its velocity squared. Well, if its velocity is 0, 0 squared is 0. 0 times the mass times 1/2 is 0. I'm going to put this through here so it doesn't look like a marble, and we know that it's the number 0. Now, as it's moving down slope, what direction coming this way is it accelerating in? Lydia.
Wait, could you say that again?
What direction, as the marble moves down slope, is it accelerating in?
Parallel to the slope?
Yes, so it has acceleration, and the definition of acceleration is change in what, Lydia?
Change in distance per time.
Displacement per time, change in displacement per time, which we could also call change in velocity, right? Okay, so it's changing velocity in this direction. When it gets to the bottom of the slope, right before it starts to go up, has it reached its maximum velocity, Lydia? In other words, as it starts to go up the slope, is it going to continue to go faster? Or is it going to start to slow down?
Slow down.
So at the bottom, it's reached what? It's
Terminal velocity.
I don't know.
Has it reached its maximum velocity? That's my question.
Oh, yeah.
Yeah. So at the bottom, KE2 equals maximum velocity. The kinetic energy is its maximum kinetic energy, okay? And it's going to equal 1/2 times m times v squared. All right. So at the top of the slope, the total energy the marble possesses equals PE1 plus KE1. At the bottom of the slope, the total energy that the marble possesses is going to equal PE2 plus KE2. Oops. I'm going to fix this a little bit. Now, this is assuming something. Everyone say, energy is conserved. Energy is conserved. This is assuming that the marble has not lost any energy as it travels from the top of the slope down to the bottom of the slope. Okay, so right here, we are assuming, this is very important, we are assuming energy is conserved. This equation if all of the energy of the marble is conserved, its kinetic energy and potential energy at the top added together is going to be equal to its kinetic energy and potential energy at the bottom added together. Would you say potential energy 1, Bryant, if it is mass times height times a constant, is the maximum potential energy the marble will ever have, or the minimum potential energy the marble will ever have?
Well, assuming that the other one's the maximum, I guess it's the minimum.
Wait, why? So the potential energy.
Oh, well, oh,
marble
never
has-
mind. It is the maximum. They both are.
Yeah, this is the maximum. So
Yeah.
PE1 is the maximum potential energy. KE1 is maximum or minimum kinetic energy.
That should be maximum as well.
It's
Right.
velocity times.
Oh, so none. It's at 0. So
so we
it's
have
the minimum.
minimum plus maximum equals maximum plus minimum. Right? Okay. So can we get rid of some of these things here? Some of these KEs and PEs in this equation? Let's give that a shot. Okay. So let's take a look at it. So PE1 plus KE1 equals PE2 plus KE2. Okay. Let's do some crazy thinking here. Which one of these two can I completely get rid of? Fev, are you here? Ethan, which two of these can I get rid of? Which one is 0? According to your drawing, which you're making. Which of these can I get rid of? The potential energy at the top of the slope or the kinetic energy at the top of the slope?
Potential energy.
Potential energy at the top of the slope is equal to the mass of the marble times its height at the top of the slope.
At the top is so then kinetic.
Kinetic energy. Kinetic energy equals what?
0.
Boom, 0. Gone. All right. At the bottom of the slope, Bridget, which of the two can I get rid of? Potential energy or kinetic energy?
Potential energy.
Because its height is now what on the roller coaster?
Changed.
Changed from some number to what?
It's changed to 0 because it's at the
changed
bottom now.
0 because it's at the bottom. Great. Okay. So the potential energy of the marble in the beginning should equal the total what at the end? Bridget.
Huh? It equals kinetic energy too.
It's equal to the kinetic energy at the end. It's so lovely. Now, this is assuming we haven't lost any energy. Do you think we're probably going to lose energy, Bridget?
Probably because I doubt that the potential energy will actually equal exactly the kinetic energy at the end.
Cool. And if we didn't lose any energy at all, would you think I could make a roller coaster that looks like this and have a marble just continue across it?
Well, it's not very realistic.
It's not
'Cause-
realistic because the marble must be losing what?
Potential energy.
Well, it's losing energy.
Well, yeah.
It wouldn't be losing potential energy in this. It would have to have the kinetic energy would have to equal the potential energy for it to get all the way back up to the same height slope. So Eli, what do you think might be robbing energy from the marble? Which force might be taking energy from the marble?
Force of friction.
Yeah. So here's what's crazy about the force of friction. It tends to steal energy from stuff, and it tends to convert the energy into a very slight change in temperature. It heats things up. And it's enough to affect the motion of something, even something as smooth as a marble can be affected by the force of friction, even on a very small slope. So, but if all things were perfect, PE1 would equal KE2. So let's write this out. That would be mass times height times acceleration due to gravity for all objects in the absence of air resistance equals 1/2 times mass times velocity squared. Okay. All right, math wizards. Lydia, can I get rid of something here?
The mass.
Yeah, mind blown. The mass of the marble is not going to affect its energy if it only had potential energy and kinetic energy. Dun, dun, dun. Okay. So this equation just got a hell of a lot simpler. If I can measure the height and I know acceleration due to gravity for all objects on Earth, okay, then I can find an object with constant acceleration's velocity, its final instantaneous velocity at the end of the slope. So that velocity there ain't an average. That's the velocity at the bottom of the slope. It's an instantaneous velocity. Don't stress. We are familiar with that. Okay. So here's what I got after I eliminate mass. Fractions suck in math. You don't like them, trust me. So what can I multiply both sides of this by, Bryant, to get rid of that 1/2?
0.5, another half.
If I multiply each side by
Or
1/2.
just two, sorry, two.
Okay, thanks. Yeah, I psyched you out there a little bit.
Yeah, I
Okay,
kind
there
of
you go. Yeah.
having a bit of trouble today.
That's okay. It's early. I get it. Okay, let's multiply both sides by 2. Boom. Okay, that half goes away. And now we have 2 times height times 9.8 meters per second squared equals velocity squared. So now I just got to take the what of both sides, Ethan, to find velocity.
The sum.
Pardon?
Sum on both sides.
Nah, nothing's being added here. What's problematic? So we don't like fractions. What else do we probably don't like if we want a simple answer? What do you call this thing?
Exponents.
Yeah, they're trash. So what could I do to this to get rid of squared? I could take what? What's the opposite of squaring something? I take the
Root.
Square root.
boom, exactly. Both of you, correct. I take the square root of both sides. Okay, now don't worry too much. Obviously, we're going to work on getting this in the Google Sheet. It is an important equation to find out that final velocity, okay? But here is what we ended up with. Here is our final equation. It is the square root. Oh, shoot, I ran out of space. You know how bad I am at that, folks. Please forgive me. So what we came up with was this. Where do I put it? I'm going to put it over here. The square root of 2 times the height of the slope in meters times 9.8 meters per second squared equals the VF, the final velocity of the marble. I know it's Friday. And everybody's like, dude, math, first thing in the morning, Friday. This is exciting stuff, though. The idea that we can, with simple velocity measurement and equations we've used before, with a new equation, we can estimate the maximum final velocity of this thing. Then we could run trials and actually compare our measurements to reality to see if the marble's losing energy. We can see how much energy the marble loses, which to me is very exciting. but I am also excited by this stuff. Okay, this is a ton. Let's make a Google document. Right now, everyone, we're going to make a Google Doc, and we're going to get these into our Google document. We're going to make figures here. And hopefully you didn't try to do the thing I did, which is where I tried to fit it all in the box, because my figures are going to look like garbage. I wish I had just drawn it on a blank piece of paper. So I will pause recording for a second. Get this recording in here. Okay, so this is what we have looks like so far. All right, we've got an introduction. You're going to share it with me, and I am going to share it with you. Great, I'm recording me taking attendance. That's awesome. And I lost connection to the school website. Oh, these technological wonders. Oh, this complicated world we've constructed. Okay. I need your email addresses. That is why I came here, so that I can share what we're working on to you all. While you're sharing your document with me at the same time. That sounded a little bit, I didn't mean that to sound condescending. I'm sorry if it did. Okay. Boom. I'm gonna make you viewers. I don't really want you to edit my stuff. Great, okay. Now I can stick this on the calendar. All right, now the next thing that we're gonna do is we're going to read this lab handout. We have some diagrams that'll help us understand what we read. And I will put my version of the Google document in the calendar, which is now shared with everyone that you can use. Okay. All right, so everybody, we are reading the roller coaster document. And it's going to actually make more sense now that we've done the diagram. I see 1, 2, 3, 4, 5, 6 of you are here. One of you is actually not here, which is going to make it hard for you to read this. And who is that that's missing? Chris, my dude, you got to open up this roller coaster conservation of energy thingamajig so you can read it. All right. Stop sharing. And